Good morning, good afternoon, wherever you may be. We appreciate you joining us for the November edition of Standard Motor Products Power Hour. Thank you very much for joining us. Today, we're going to talk about gasoline direct injection. My name is Darren Beanard. I'm going to be your instructor. So let's get into the information. Now, what are we going to talk about today? Well, our learning objectives are the low pressure and high pressure fuel system. We're going to discuss those two parts of the system. We're going to use scan data today for diagnosis. We're going to see how it is our scan tool is going to offer us information that would lead us in the right direction when we're diagnosing faults. We're going to emphasize safety as well. You'll notice safely servicing the high pressure fuel system with an exclamation point. Yeah, we're definitely going to emphasize safety because there is a potential that we could actually get seriously hurt if we don't follow the right precautions. We're also going to look at component replacement tips. What do we need to keep in mind if we're replacing parts on the system? Now, to begin our discussion, let's start out with a situation involving this 2009 Chevy Cobalt with a 2-liter GDI engine. Now, this vehicle has a problem where the owner, as they're driving along, suddenly will have a severe power loss situation. So this engine loses power at times. In fact, it falls on its face. It won't get out of its own way. So the owner is actually afraid to drive it. So they had it towed into the shop. Now, the technician, when he went out to the yard to get the car and he brought it into his bay, he felt like the engine seemed to be running okay. It idled fine. Then when he was driving into the bay, it seemed to be doing okay. He raised the hood. He looked around underneath the engine compartment, didn't really see anything out of place, nothing wrong. Well, the next thing the technician decided to do was connect his scan tool, and he took it out for a test drive. He recorded data. Now, I don't know if he scanned for codes. He didn't tell us. Seems like he probably should have, but he didn't tell us about it. And I'm not going to arbitrarily add to the story because, frankly, I don't know. But I do know that he captured the data here during his test drive, and there is going to be a fault that will occur during this recording at some point in the data. In fact, that the information that he's going to get from his scan tool here is actually going to give him enough information that he's going to know where to go with his diagnosis. Now, currently in the image where the cursor is, we see that the numbers here are reflective of where the cursor is. We've got plenty of power. He's accelerating. You can see the engine RPMs are going up, 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 up at this point. You see the reason why, because he has his foot buried into the carpet. He's got the gas pedal all the way to the floor. He's wide open throttling this thing. We have plenty of fuel pressure. You see, we have around 2,150 PSI of fuel rail pressure. The vehicle speed is going up, up, up. We're increasing in speed. But what happens a moment later? Well, right here, you see something happened. Our fuel pressure just completely fell off. And you can see the engine RPMs are now going down, down, down. Now, that's not because he let his foot off the gas. He has his foot buried into the carpet still. But, the engine RPMs, the vehicle speed are going down, down, down. Because why? Because our fuel pressure dropped to just below 50 PSI of pressure. So what happened? Well, the answer to that question is going to lead us directly to the diagnosis of what has failed. Now, the technician knows at this point where he needs to go with his diagnosis, and maybe you have a good idea of where we need to go. But now at the end of the session, we will all know exactly what to do. So now let's go through gasoline direct injection. And then at the end, we're going to come back to this car and we're going to fix it. Okay, so first, what is GDI? What is gasoline direct injection? Well, simply put, it's a system that allows us to inject fuel directly into the combustion chamber under very high pressure. Now, maybe at idle, we might have, 175 to 200 PSI of pressure. That's very common. But then as we drive the vehicle down the road, we might see pressures of 1,500, 2,000 PSI, maybe even over 2,000 PSI, depending on the current load that's being demanded on the engine at that particular time. Now, why did the manufacturers go to this? It's because this system, gasoline direct injection, has some advantages over port injection. Matter of fact, there's actually advantages on both sides of the spectrum between port and GDI. But GDI actually is one of the methods by which the manufacturers were able to get more power out of a smaller engine and therefore able to meet the ever-increasing emission standards. So that's something we've seen that manufacturers have gone all in on in the last few years for that reason. Now, in reality, with a gasoline direct injection system, we can say that there are really two fuel systems. We could say that there's a low pressure fuel system and there's a high pressure fuel system. So let's kind of fuzz out half the image and let's talk about the low side of the system for a second. Now, that's our supply side. Now, on this side of the system, we have a fuel tank, of course, with fuel in it. We have an electric fuel pump in the tank that's going to deliver low pressure supply side fuel to the high pressure or to the inlet side of the high pressure pump. And so we have, of course, all of the lines are associated with this. Now, on this side of the system, we're going to expect there to be maybe 50 to 80 PSI of pressure, generally speaking. I know there's a few applications out there, like, for example, when I was a Ford tech, we would have some Ford Focuses that had about 90 PSI on the low side. There's some VW Audis out there that might have about 100 PSI on the low side. But the bottom line is we're going to have a fuel pressure somewhere in that range on the low side of the system. That's our supply side pressure. Now, over on the other side, the high side, that's where all the magic happens. We're going to ramp up that supply pressure up to anywhere from maybe 175 PSI or so at idle to maybe on up to about 2,000 PSI or even more than that under heavy acceleration. Now, we create this high pressure using a mechanically driven high pressure pump that's bolted to the engine. Now, some cars might have two high pressure pumps, one on each side of the engine, but most engines are going to have just one high pressure pump. So they'll have one low pressure pump in the tank, one high pressure pump out in the engine bay. Now, this high pressure pump is going to be driven by a set of lobes on the camshaft. Now, we're going to take a closer look at that in a few minutes. So then we're going to deliver that high pressure fuel to the fuel rail, where it then will be distributed to each injector that corresponds to each cylinder. And so we're going to use that method to deliver fuel into the cylinders. Now, you may wonder, why do we need all of that fuel pressure? Well, it boils down to this. Contrary to what some may have thought, I know myself as a technician years ago, in the Ford dealership, when we first started seeing GDI, my misconception was that they were overcoming engine compression. No, we don't inject fuel on a gasoline direct injected engine like we do on a diesel engine. A diesel engine, you inject it at the last moment right there when the piston reaches its apex of the compression stroke. But that's not what happens in a GDI engine. On a gasoline direct injected engine, we're actually going to inject fuel, most often inject fuel on the downward intake stroke. So as that piston's on its way down, as that intake valve opens, that's when we're going to inject fuel on a GDI engine. Now, there is no compression in the cylinder at that moment. In fact, there's actually a vacuum in the cylinder. Well, why do we need the high pressure? Well, it really boils down to this. First, we need good fuel atomization. If you think about it, we've got a very, very limited window of time in order to mix the air and the fuel completely. So we only have that brief moment when air is rushing into the cylinder during the intake stroke to fully mix. We've got to have a complete breakdown of the fuel particles at the injector tip. And because of this, GDI injectors are designed with exceptionally small spray ports at the tip. So we need that high pressure. And the other reason is, of course, the very narrow window of time. We only have the time that it takes for that piston to complete its downward motion during the intake stroke to get all of the fuel into the cylinder. So in fact, the faster the engine is turning, the higher the RPMs are, the faster the piston is moving, so the less time we have. So we have a very, very small window of time. Now, just to establish that we are in fact delivering fuel in the intake stroke, here's a lab scope capture where we map the piston strokes along with the ignition coil and the injector events. And you'll notice in that green channel right there, during the intake stroke, that's when the injector event occurs. In fact, it occurs very early in the intake stroke. The injector pulse width at this point is only about a millisecond. So at idle, that's typical in a GDI engine to have a very, very small amount of pulse width on the injectors. About a millisecond is typical. But then when we increase the load on this engine at higher RPMs, we do see an increase in injector pulse width, to about 3 milliseconds, but that's really only adding another couple milliseconds. It's not really that much of a difference. Really, the difference, though, now is in the pressure. So as we need more fuel into the cylinder, we're going to increase the volume by the pressure control. And you'll notice here in this scan capture from this engine, you'll notice this bottom PID down here, that our fuel pressure here is very, very dynamic. You see that graph is going up, down, up, down, up, down. At the moment where the cursor is, we have about 1900 PSI of pressure. But if we could move that cursor over to the left, which I can't, I wish I could, but you'll notice here that we have a point where at low RPMs, we only have about maybe 600 no, I think it's a couple of hundred PSI of pressure. We don't have a lot, but look what happens a moment later when we increase the engine RPMs to about 6,000 or 6,700 RPMs or so. You see the pressure ramps way up to close to 2,000 PSI. So we have a very sudden increase in pressure. So the bottom line is, how we fuel a GDI engine is primarily controlled by the dynamic changes in fuel rail pressure. Now, going back to the low side for just a moment, I think we all probably understand the low side part of the system. Why? Because it's the same basic supply system that we've had for years with port injection. You got an electric pump in the tank, like you see here, and everything that we have come to know about the fuel supply on a port injected engine, we can apply to this low pressure side of the GDI system. But now what about the high pressure pump? Now, obviously, we need to fully understand this as well. Now, the high pressure pump is a single piston mechanical pump that is driven by a set of camshaft lobes. Now, located between the camshaft and the pump is a follower that you see here. Now, that follower looks like something you might see on the valve train, right? Well, that is used for this application here as well. Now, it's important to know that that follower is there, and it's important to pay attention to it because very commonly we do have these followers that fail, and that would cause a high pressure pump delivery problem. Now, here's an example from a 2007 VW Passat with low engine power, along with very low fuel pressure. Now, when the technician removed the high pressure pump, he looked, you can see that the high pressure pump, that push rod is actually broken, and you see the end of it is damaged. Well, when he looked down inside where that pump or where the lifter is, right here in that hole right there where the lifter is, you can see that the entire center portion of that lifter is actually gone, and you're looking down on top of a damaged camshaft. So there's some serious engine damage here that needs to be addressed. And no doubt there's probably even some sparklies floating around in that engine oil, I would imagine. So that said, we've got quite a bit of damage here that needs to be addressed. Now, mounted to the pump is a solenoid that's commonly known as an FVR, or fuel volume regulator. Now, it's used by the ECM to control the output pressure of the pump. Now, the ECM is going to do this by controlling a pulse width to that solenoid, and the solenoid itself will control the output of the pump by controlling how much fuel we allow into the pumping chamber of this pump assembly. So the more fuel we have in the pumping chamber, the more pressure we can expect to be delivered by the pump. So the ECM is going to be in control of this solenoid, and you can see here in the bottom right-hand corner a lab scope capture of the pulse, or rather the duty cycle that is going to be sent to that solenoid by that ECM. And now the timing of this control is very, very precisely choreographed with the camshaft. Remember, we have these camshaft lobes that are going to be operating that pump. And so, often the ECM has to assume that the engine is mechanically sound and that the camshaft has the correct timing as it operates this fuel volume regulator. But now, if anything disrupts the choreography between the camshaft timing and the operation of that solenoid on the pump, then we can have problems that can occur. Here's an example on a 2011 Chevy Equinox with a 2.4 liter engine. There were codes that kept setting in the ECM We had a P0016, which makes reference to the correlation between the crankshaft and the camshaft. In other words, that P0016 is saying, hey, we got an engine that's out of time. But then notice these other two codes. We have a fuel system performance code, and well, we actually have two fuel system performance codes. We have a P0089 and a P228D, which both have to do with high pressure fuel system control or performance. Now, it may seem like these are completely unrelated problems, but now we want to consider the fact that the high pressure pump is driven by the camshaft. And if the engine has jumped time, it can certainly affect the ability for the ECM to control the high pressure delivery, the high pressure pump's ability to deliver its proper pressure. So in this case, it was all related back to the fact that the engine had jump time. That P0016 was actually telling us what was wrong. We have a timing problem, a base engine timing problem. So we need a timing chain set. So we really need to understand the interrelationship between the mechanical timing of the camshaft and the high pressure fuel pump that it's driving. So now what if you run into a drivability concern on a GDI vehicle and you find that you have a fuel pressure issue? Maybe you've reached some kind of crossroads in your diagnosis and you're trying to figure out, okay, do I need to go over here to the low pressure side or do I need to look at the high pressure side? What can help you to figure out what direction you need to go? Well, one key tool that's going to be very helpful is your scan tool. If we use scan data appropriately, if we record scan data and we're able to capture the fault, we very often will find clues that can help direct us to what direction we need to go to send us either to the low pressure side or the high pressure side. For example, here's a capture from a situation where we had a vehicle that the engine was stalling out. Now, at the point of the cursor, we can see that the engine RPMs right here, where the cursor is, the engine RPMs have dropped to 0. Yeah, the engine stalled at this point. Now, fuel rail pressure had dropped all the way down to what looks to me like about 0. Now, I do see an increase in fuel pressure, and that's because the engine is sitting here static. We have heat in the engine bay, and there's some residual fuel in the fuel rail, so we have that trend up in fuel pressure on the rail. But that's just because of the heat in the engine bay and that pressure that's building in the rail. If you look over here to the right of where the cursor is, it looks like we have numerous attempts to start the engine. And finally, over here, you can see that we're not able to get the engine running at all. However, we have 0 fuel pressure, completely 0. In other words, we've run out of fuel on the rail. Now, is this caused by a low pressure pump or a high pressure pump failure? Which pump is causing this? Well, as it turns out, in this case, it was a low pressure pump problem. How did the scan data show this? Well, because we can clearly see the pressure's dropping to 0 or near 0. This is a clear indication we're losing our fuel supply. We're running out of fuel. Now, that doesn't mean we're out of fuel in the tank. Well, there's plenty of gas in the tank, but that gas is not being supplied to the high pressure pump. Our low pressure pump is at fault here. It's not giving us what we need to generate any sort of fuel pressure. That's the problem here. Now, what about this vehicle? Here's a capture from one that lacks power. You can drive the car. It's a struggle, but you can do it. The scan data, when the scan data was recorded during the event, during the fault, we see that we have about 76 PSI of fuel pressure, and it's pretty steady, isn't it? That's the expected supply pressure on this vehicle. We should actually have several hundred PSI of pressure under the conditions we see the vehicle being operated under. It's clear that the low pressure pump is delivering, but the high pressure pump is not increasing the pressure to a level that it should. So the problem here is a high pressure pump. That's what's failed. The low pressure pump is giving us the supply, but the high pressure pump is not increasing the pressure. Now, in most cases, when we have this type of failure, the low pressure supply will simply pass through the high pressure pump and feed onto the rail, just like we saw here. And that's what's happening here. When it does, and in a lot of cases, the car will run, and you might even be able to drive it with some effort, but you just won't have the power that you should out of it. Now let's look at safely servicing GDI. Let's spend a few minutes here together discussing this. Let's say you've diagnosed the concern, and now you're ready to go to work on the car. Well, we always want to exercise safety when we're working on these systems. What do we mean? What dangers are there? Well, here's a danger: pressure. So here's an example from a GM 3.6 liter that we did some testing on. We ran this engine only for about 5 minutes. So over here off the screen, just imagine we ran the engine for about 5 minutes. And at the beginning of this capture that you see here, that's right where we shut the engine off, right there. We shut it off. Now, that could be likened, that 5 minutes that we ran that engine could be likened to the period of time that it might take you to go out to the yard and bring a car into your bay, okay? So just picture that. Now, we shut the engine off. Now, at the point where the engine was actually running, we had about 600 PSI of fuel rail pressure. But what happened when we shut the engine off? What happened to the fuel rail pressure? Well, it started increasing, climbing, going up, 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 up. In fact, after about 20 minutes, which you could liken that maybe to the time that it took you to pop the hood, raise the hood, and go start gathering up your tools. You're ready. You are ready. 20 minutes later, you've got your wrenches in hand and you're ready to break tension on that fuel line, that high pressure fuel line that you're about to take loose. But guess what's on the other side of that connection? Waiting for you inside of that line is over 2,300 pounds of fuel rail or fuel pressure. Let me tell you, folks, that fuel is not going to come out of there like a razor blade. No, no, no. It's going to come out of there like a sword. So we need to depressurize the system before we start any sort of repair on a system like this. So how do we do it? Service information should give you a recommended procedure for depressurizing this system. But what it's going to boil down to is this. We need to disable the supply pump, start the car, and let it run out of fuel till the engine shuts off. Now, if you remember a few minutes ago, what we showed you, what happens when the supply pump stops working, we go to zero pressure with maybe a little bit of residual pressure left in the rail, but it's going to be very, very little. So how do you disable the fuel pump? Well, maybe you can use your scan tool. Maybe there's a function on your scan tool that you can do that with. Maybe you unplug the fuel pump control module and start the engine. Or maybe you remove a relay or a fuse to disable the low pressure pump. And once you do, start the engine and watch the fun. You can see in the data that the pressure eventually was depleted from several hundred PSI down to about 29 PSI. Clearly, that's a much different situation. This thing is safe to work on. All right, well, so now let's take a look at some component replacement tips. Now, let's say you're going to replace something like maybe a high pressure pump or something like that. Well, I have over here in front of me some parts. I'm going to show you some things on with the parts I have in front of me here. But we notice here on the screen that we have two examples of a camshaft in different positions. We're saying the one here on the left is incorrect. Well, what's the deal? Well, this is discussing replacing the high pressure pump. And of course, we know that we have these cam lobes right here. And so if we try to install a high pressure pump against the high point, this high point on the lobe, we're going to find ourselves battling a very, very, very powerful spring that I'm going to show you in just a moment. So what we really want to do is install the high pressure pump on a low point on a low. So we want to index the engine into a position where the camshaft is on a low point so that it is that we can install a high pressure pump. So let me step over here and show you what I'm talking about. Now here's this high pressure pump you see here, and there is a very, very powerful spring. So if we're on a high point on a cam lobe, we would be battling that spring to install it. And in fact, of course, we have these mounting bolts right here that we would probably be using to pull that pump into place. Well, in that case, again, if we're on a high point on a lobe, we could actually warp or damage the housing of the pump. We could actually pull the threads out of the aluminum cylinder head that we're bolting this thing to. So that's going to be a concern with regard to the installation of a high pressure pump. Another thing that we want to keep in mind is that whenever it is that we have that high pressure pump out, we will want to pull this follower out and take a close look at that follower. We want to look it over for damage, because any damage that we see on that follower, there will be corresponding damage on the camshaft. So when we see damage here, that indicates that we have maybe deeper problems in that engine. Now, what if we're replacing a fuel injector? Well, of course, if we're replacing a fuel injector, when we pull the fuel rail off, let's say we're replacing this fuel injector right here, that means we're going to be pulling the entire rail off, and we'll have all of these other injectors that we may not necessarily be replacing off as well. Well, once we remove these injectors, any injectors that we're not replacing, we do have to replace the seals on them. Now, these are special Teflon seals. So in order to replace those seals, to take the old one off, we can just use a pair of needle nose pliers. I'm not going to actually do it, but you would pinch that seal, and it would clearly break, or easily break, that Teflon seal off of there. And then to replace the seals, we have some special tools. There's a special conical shaped guide that we would put in place, then the Teflon seal, and there's a special pusher tool that we would push that up onto its land in order to install it there where it needs to be on the land. Once we do that, then there's a special sizer tool that we would use in accordance with service information. We would size the seal. Service information will tell you exactly how to do that. But there's a tremendous number of one-time use components. If we did remove the injector from the rail, we would also be replacing a spring clip and any other seals and spacers that there are on the top of the injector. There is a seal here, and there is a spacer here on the top of the injector, as you see on this example that I have right here. There are also some other one-time use parts. We would be concerned about perhaps any high-pressure lines. High-pressure lines are going to be something that would be just one-time use. Once you take it off, you do throw it away and you replace it. Some manufacturers, like GM, even use a yellow tag on these lines just to remind you that if you take this thing off, you're going to have to replace it. Now, you'll notice that I have in front of me some parts, and they look like they've been installed on vehicles. Well, in fact, they have. These particular parts have. We have on the other side of this wall from our training center a testing facility where we have a team of technicians. And whenever it is our engineering department designs a component or a part, we actually install our parts on vehicles that we have in our testing facility, and we actually run them under real-world application for further testing before we actually put the part in the standard brand box. So that's added reassurance to you technicians out there that when you use Standard Motor Products parts, you are using parts that have been truly tested under real-world conditions. Now, before I go back to my computer, I do want to make one final point, and it is this. Any of these bolts that we are, of course, installing, well, there'll be replacement bolts. We want to make sure we're always torquing everything to specification. Make sure we're following service information and torquing everything. You can count on everything having to be properly torqued. Okay, well, let's get back to our subject. Let's get back to the car. We're going to end the day with this car. If you remember, we started the day with this car, so we're going to end the day with this car. And again, this was this 2009 Chevy Cobalt with a 2-liter gasoline direct injected engine. If you remember the problem was that this thing would lose power at times. In fact, as we said, it would just fall on its face, and it would do so suddenly. Now, you remember, of course, the technician was driving the car along, and it was doing okay until all of a sudden, again, we had that sudden drop in fuel pressure in an instant. So where would you look for the problem? Well, let's think about this for a minute. Are we dropping all the way to 0 PSI? Are we dropping completely to 0? And the answer is, well, no, we're not. In fact, we're dropping to about 50 PSI, which we could probably say is very likely, it sounds suspiciously like low side fuel pressure, doesn't it? So it looks like our low pressure pump, our supply pump, is actually working. Yeah, and we're delivering fuel up to the high pressure pump, and that fuel, of course, is being sent right on through the high pressure pump, but it's not being increased, or the pressure increase is not occurring, which would be the job of the high pressure pump. So what's failed on this car? In this case, the technician found that it needed a high pressure pump. It's probably, I'm going to say it's probably that solenoid right there. There's probably some kind of intermittent problem with that solenoid given the sudden nature of the failure. Usually if you have a mechanical failure in a pump like this, it's either going to work or not. In this case, it works and then it doesn't. So it's probably that solenoid is probably what's causing it. But you know what? It doesn't matter. This is a buy one, get one free situation. That guy comes as a complete unit right there, pump and solenoid together. You don't separate them. You're going to get that guy right there. Now, of course, he probably also replaced the follower. I'm going to make that assumption as well. All right. Well, that was great. So what did we talk about today? Well, today we discussed the low pressure and the high pressure fuel systems. You'll notice we broke them down. We showed you how they have they're two separate pumps or two separate systems. Our low pressure system is going to have about 50 to 80 psi. Maybe in some cases it might be a little bit more than that. High pressure fuel system, we're going to deliver using a high pressure mechanical pump. We're going to deliver anywhere from a couple of hundred psi, maybe up to about 2,000 psi to the fuel rail, which will then be sent through the injectors. We looked at scan data. We saw how we can actually use scan data to help direct us in the proper direction. Is the problem on the low side? Is it on the high side? We actually saw it in scan data, didn't we? We emphasize safety. We want to make sure nobody gets hurt working on these systems. Just remember, there is the potential for that really super high pressure fuel that could be on the other side of that connection that you're about to take loose. So use safety. Make sure you don't get hurt. And then we looked at replacing components. We discussed some of the tips involved in replacing components. Now, I would like to also make mention of our YouTube as I close out. I'd like to make mention of our Standard Brand YouTube channel. I invite you to go to YouTube, type into the search box Standard Brand. That will take you to our YouTube channel where we have a lot of very, very helpful videos, things that will help you. There's a lot of tech tips. There's a lot of installation tips and explanation of how systems work, very similar to what we just talked about today. Many of the videos are very short but yet very informative. So I think you'll enjoy going there. So I'm going to recommend that. All right, with that, I'm going to now ask my production manager, Mr. Corey, Corey, do we have any questions from anyone?
It would appear as though your content was very thorough and to the point there, Darren. We do not have any questions, and so I will let you close us out, sir.
Well, thank you very much for joining us for our class today. Thank you for spending this time with us on the SMP PowerHour. This was our November class, gasoline direct injection. I was your instructor, Darren Beanard, and we look forward to seeing you again. Thank you.